Okay, is it all good? Everyone can see this screen? Perfect, thank you. Okay, let me share the link on the chat. Of course, you can find this slide on our Google Drive, but also you can use the chat as well. But before we start, let me explain you a little about hydroelectric power. What is before we start the hydroelectric power, let's just recap what we learned during the last 4 weeks. Okay, first we learned how to build pipe-saw model itself, right? When we start to use pipe-saw, we need to start defining the network using pipe-saw, that network, right? And then we need to set the snapshot. Here, snapshot means the time frame that we are going to use. It can be yearly or monthly, weekly, or hourly, whatever you like. But you can set it up as, usually you can set it up as a hourly set, and then you can decide to choose what kind of a resolution you want to use or granularity you want to use. And then we can add carriers, which is a group of fuel sometimes, or group of emissions, or whatever you like. It's basically a group or classification of anything you want. And then we can add buses. Buses are node, right? Each bus can have generator, demand, or electric storage, or hydroelectric power, or anything you like. But the thing is, whatever you define, whatever the generator or ESS demand you define, these must be linked to the bus, right? And then you can connect bus to bus using link or lines, right? You cannot connect generator to demand, right? In pipe-saw, you always need to connect those components to the bus, and then connect each buses to each other. That will represent the transmission in pipe-saw. And we can set different values such as Pmin PU, or ramp limit up, or min up time, or min down time. And then we can set this pipe-saw algorithm to be committable or non-committable. When it is committable, it is that means that pipe-saw can decide to turn on or turn off the machine or the generator, right? And we can also let pipe-saw to decide the capacity using pnom extendable as true. If we set pnom extendable as true, then pipe-saw will decide the capacity of the generator based on the cost optimization. When we say cost optimization here, pipe-saw will use both investment cost and the marginal cost as well. And also later today, we are going to cover some more constraint that will include a global constraint, and then some other cost constraint as well. Go for hydroelectric power. What is different with what is the difference, or what is the unique component of hydroelectric power compared to other generators, or maybe compared to other demand, or etc., other component? First, when we define hydroelectric power or ESS, we don't use generator component, but we use storage unit component. So in this storage unit, we can have inflow, and also we can have, let me just double check. Yes, we can have inflow, which is a time series data that representing the water inflow into the reservoir, right? If you think about the hydroelectric power, hydroelectric power cannot generate electricity if there's no water, right? So that inflow actually mimic the natural water inflow to the reservoir. However, this inflow doesn't mean it's about the volume or quantity, it's about the megawatt, right? So you need to calculate by yourself the amount of water to megawatt hour equivalent. And then we have cyclic state of charge. So when the cyclic state of charge, this is very critical one and very important one that you need to remember. If cyclic state of charge is true, then storage unit will have the same start and the same start and end amount. So for example, if this generator or this energy storage start with 50% of charge initially, then in the end, it must be 50% of charge as well. Otherwise, this system will somehow use certain amount of free energy, right? So for example, if the battery, when I say start and in end, this means the start of the entire modeling period and the end of the entire modeling period. So if it's 2017 data set, or 17 is the modeling period that we want to cover, then start is the first hour of the 1st of January in 2017 or 2017. And the last hour or the end is going to be the last hour of 31st of December 2017, right? So the level of the storage should be matched, right? And then there is efficiency. So somehow energy storage always lose the energy. Even hydroelectric power lose energy because evaporation, or because in case of pumped hydro storage, you need to pump it up, right? That it uses energy, so lose at least about 40 to 50% of its energy, right? And ESS also lose the energy. In terms of battery itself, it almost does not lose the energy because it's very, how do I say, highly efficient. However, when we see the entire system, it loses about 10% roughly. So that's how it goes. And then we also have a efficiency dispatch. So this is the lose amount of energy loss when the energy storage generate electricity, right? Even when energy storage generate electricity, even if it has a certain amount of energy already stored inside, it still needed to run the turbine, or sometimes it needs to go through some resistance, right? So it has a certain amount of efficiency, which is very technical thing. And then there is a state of charge initial, which is between 0 and 1. If you set it 0, this energy storage will not have any single stored energy initially, right? If it's 1, it will start with a full charge. So this is something that you need to set up carefully based on actual data, usually, but not always. If you are not sure how much, then it's safe to leave it as a somewhere between 30% to 50%. Usually, it's just safe amount, because about 30% is not too high. When we see it as a free energy, it's not too much, but at the same time, going zero amount of energy, stored energy is very unlikely in many energy storage system, right? Even you don't want to juice out the entire energy from the system. So that really doesn't happen much. So we are going to add the storage unit, which is hydro reservoir, to bus 2, and then we are going to create this kind of network. Okay, let's go through just one by one, and in the end, I'm going to share my code to make sure that everyone has the same starting point. Okay, just see, big enough, I think. And then let me have the comment. Let me have the chat on my screen to make sure that I can see any questions here. And let's build it. So first thing first, we need to import pipesa, and then we need to import pandas spd. It's just automatic thing. Always you need to use it. And then we will set up network using pipesa network. If you can just do it on your, you can do it together. You can just type it together on your own Jupyter Lab or Jupyter Notebook. If you are not available, you can just have a look at it, and then in the end, you will have my code. And then we will set the snapshot, which is date range 2024, the first day until 2024, last day, 11 p.m. And its frequency is H, which means hourly. We will have two carriers. We will add carrier as gas, carrier as bio. And then we have the demand data. For those of you who don't have the demand data, you can download it in the data on our Google Drive. Demand is in CSV file in the data folder, data directory, demand 2024.csv, and its index column is the first one, and the first column is date. So we set it parse date as true. And then we are not going to see each head because we already did it. And we are going to add buses now. Bus, let's say bus 1, bus 2, bus 3. And the capacity of the load is 100 megawatt. And we are going to add the load to where? To bus 1. And each capacity, I mean, the load, the pattern, the load pattern or demand pattern is going to be demand capacity vector. I can just type the name because I remember the column name, multiplied by max capacity. And we need values. So this means we are going to add the load, and the demand data has the capacity factor, which is between 0 and 1. And we have the maximum capacity in megawatt. So the maximum capacity is going to, maximum demand is going to be 100 megawatt. And probably the lowest one is not going to be 0, but probably, I don't know, about 50 or 60 megawatt or something like that. So then we are going to add, we are going to limit the snapshot to the first 20 days. Otherwise, it takes too much time. And we will add gas generators. Gas 1, 2, or 3, and each capacity is 50 megawatt, and it can generate Pmax PU, generate up to 100% of its capacity. And its marginal cost is 50. Usually, we assume it's dollar or euro, but doesn't need to be too much Western, so you can choose whatever the currency you like to. But the thing is, it's per megawatt hour. Carrier is going to guess. So we can copy and paste one of these, and we will add it to guess 2, which is slightly smaller one and slightly cheaper one, right? Is it all good, or am I going too fast? This is just reviewing the previous 4 weeks, so I think it should be fine. Okay. So nobody is answering, so I think I assume it's all okay. And we are going to add bio. I just added one more. Let me double check it. Right, it's moving, right? Okay, it's moving. It's not my problem now. Okay, thank you. You almost freaked me out. I thought I was the only one seeing my screen for about 10 minutes. Okay, we are going to have a bio here now. I just copied and paste another gas, and bio need to go to bus 2, and it's 40 megawatt, and then its marginal cost is 30, whatever the currency, and it is going to be a bio. Carrier is bio. And is this all? No, actually, we need a little more. What we need to add link. Again, I told you that this can be lines or link. The only reason that I use link is because link is much simpler way of adding efficiency, but lines are much more sophisticated and much more realistic way of doing it. However, explaining you how to use lines, I mean, the concept of lines is very complicated because you need to understand AC, not just the DC. So I'm just using link. And mostly when we talk about policies, link is just more than enough. Okay. Almost the only reason that you need the lines rather than link is because is when you need to analyze its proper power flow. But in policy analysis, it will not happen. Mostly it's very technical thing. And bus 0, which means the first of all bus is bus 2, and bus 1 is bus 1. So it will flow from bus 2, bus 1, or also the other way around as well. The capacity of the bus is 100. Efficiency is 0.9. So when we flow the electricity through this link, we lose about 10% of electricity, right? And then we will copy and paste the link. We will connect 1 and 3, which is exactly the same, but connecting bus 3 to bus 1. Then we are going to add some other information. Network generators start up. Probably we don't need a startup cost. Let's set just a payment view. Network generators Tmin Q equals 0.2, which means if generator is on, it must provide at least 20%. Oh, thank you so much. At least 20% of its capacity. So somebody is following. Thank you, Paulo. And network generators P ramp limit up is 0.2. So every hour, each generator can swapping bus 0 and bus 1 will not give you any differences in this because link allows to flow to both sides. But in case of lines, it can be different depending on how you set it up. So ramp limit up means this generator can increase its capacity about 20% of its maximum capacity every hour. So if it's 100 megawatt, every hour this generator can increase its capacity by 20 megawatt. And then network generators mean up time is 5 and its mean downtime is going to be 2. Let's see this works fine. There is yeah. Warning, there's warning, it's fine, all fine, blah, blah, blah. What we want to see is, okay, it's optimal. As far as it's optimal, so far this version is working totally fine. So let's go back, and then we are going to add some more to make sure this is much more realistic. So now what we want to see is what we actually did in the previous course was generators P norm is 0. We set the generator's capacity as 0. Why? Because we wanted to make pipes to decide its capacity. Generators P norm extendable is true. Then pipes will decide its capacity, right? However, to make sure that pipes decide its capacity, we need to add some more information, which is capacity, basically investment cost. Network generators, ROC, in case of gas 1, which capital cost equals 800,000. And then we will have gas 2, and we will have bio as well. In case bio, let's say 7, case gas 2 is 700,000, and bio, let's make it a little more expensive. And let's try to optimize it. Does it work? Yes, it's optimal. As far as it's optimal, I think it's all fine. We can add some more information. What can we add? We can add P min and P max. Let's go for gas 1 first. P min equals 10. I can paste it and change it to max. It's 80. This means gas 1 generator can gas 1 generator's capacity can be as low as 10 megawatt, but as high as 80 megawatt, right? We are setting up some sort of limit of this optimization process. And in case of gas 2, it can be, let's say, 5 to 60. And what about bio? I say between 0 and 5. That's the amount that pipes can decide. Gas 1 need to be always between 10 and 80 megawatt. Gas 2 is 5 and 60. Bio is 0 and 50. We are running a capacity expansion optimization at the moment. And then before we run it, we can add one more carrier. Probably you already noticed, but I'm doing what we learned, what we had gone so far for the last 4 weeks, just a step by step, right? Not everything, but mostly we are going to add generator, which is solar, one of the popular one. Carrier is going to be renewables. And then we are going to connect it to bus one. And each capacity is going to be 20 megawatt. Capital cost is going to be 500,000. And we will have wind as well. Wind. This time, let's make it 15. 500,000. In the last course, I provided a PV and wind profile data set, which is basically the capacity factor. And we can call it PV profile equals PV. I think I have this code from the last week. Yes, I found it. Because I don't want to write this long part again. This is from the last week. We import PV profile from Ninja PV.csv and Ninja Wind.csv, and Hyunwoo actually threw me a quite a good observation-based question. He said there is some strange solar PV generation around at dawn, or down, whatever. The problem is, I know there are always data issues. Wherever you download the data, it always has an issue. So you need to make sure that this data is correct. So you need to check the data integrity. That's very basic thing. But I didn't do it for this course because data integrity is not a big matter for this course at all. But what we are doing is just trying to understand how this system work and how this pipes system actually work, right? So that's why I didn't do the data integrity, so the data can be slightly strange. And let's run the model and let's see the result. So we have a proper code now to start with. So this code basically gives you the capacity. It will give you the capacity, something like this: network generators, pnom opt. Pnom opt is optimized pnom, so optimized capacity. So we can just, if we type it, network generators dot, not underscore, pnom opt is gas 1 is 50 megawatt, gas 2 is 30 megawatt, and bio is about 40 megawatt. And then we have 20 megawatt of PV and 15 megawatt of a wind. This is what we have. And then we can also get some investment cost as well. Yeah, this is how, or this is what we learned so far. I'm going to copy and paste my code to the slide, last page of the slide. So no, not the last page, sorry. Page 5. This can be pretty long. So please copy the entire code. It's on page 5. Go to page 5, please. And then copy the entire code. Put it to your first cell, and then run it. The most important part is the last one should be okay, optimal. but it will be all the same as far as you have the data in the correct data folder. The structure of data folder for me is just the data, nothing else, just data. And then in the data folder, I have all the data set required here. So if you have different data folder or if you have different name, then you can change the name of the data folder to data or data, or you can change the code itself. I'm gonna wait about a minute to make sure that everyone has everyone's on the same page. Okay, we have one person working. Can you thumb up if it works for you? Thank you, Amanda. Okay, seems it all works with almost everyone. Yep, I'm waiting. Paris, don't worry, I'm waiting. So far, I think 5 or 6 people. So I'm gonna wait a couple more people. Let's make it to 10. Okay, great. So let's move on. And after about 10 minutes, we are going to have a break. So while we are having break, let me know if you have trouble. Okay. First thing first, we want to print out our result. So I provide you a simple sort of function because it is a little more interactive, but easier. I'm going to sharing an easier way to plot the chart. First, we can start, okay, let me just write it from the beginning, from the network. And what the information we want to have is in generators T, which means temporal information, time or temporal information. And then what we want to get out is power. So it's P. And we can plot it. If we just plot, it will be something like this. It's a line and it's not really, how do I say, distinguishable, right? So usually what I set is kind is area. So turn it, I make sure it turn to area chart, and then state is true. If you set type this, then it will be look like this, but it seems it's too, how do I say, too high. So we can set big size, that's to be 12 and probably 6 like this. Seems better, but maybe slightly narrower. Okay, this looks better. We have gas 1 and gas 2 generator, and we have bio, PV, and wind, which is providing the electricity whenever it requires. As we can see, gas 1 and gas 2 are basically a base load and intermediate, and then there is a small amount of bio when it is only required. Probably when the gas 1 and the gas 2 cannot provide enough backup due to transmission limitations. So now we are going to add hydroelectric power here. As I said, we need to add another one, but not generator, just storage unit. And we are going to name it hydro reservoir. Is it reservoir English or French? Sounds like very French to me. But two. Thank you, Paulo. Yeah, I expected it. Reservoir. It sounds too elegant to be English. Plus two. And then its capacity is 50 megawatt. Storage capacity is 50 megawatt. And then we're gonna set it extendable force. We're gonna just set this capacity as 50 megawatt, nothing else. Max hours is 12 hours. Technically, you don't need to set it because this is hydro reservoir. However, at this time, we are going to set this as a max 12 hours reservoir. Capital cost is 100. Usually much more expensive than 100,000, but it's just a test. Marginal cost is gonna be 0. In many cases, renewable and energy storages actually don't have marginal cost because it does not need fuel. However, in real world, definitely it needs operation and management cost, which needs to be included. Efficiency store is gonna be 1. I'm going to set just there is inflow, which doesn't require additional power to store the water, right? Efficiency dispatch is going to be 0.9. It's 90%. Cyclic state of charge is true, so that the start and end point of this storage unit must be the same. And then state of charge initial is 0.5. So start with 50% of charge. And Pmin, Pu is 0, so that it can basically generate electricity whatever it wants to provide, which is not likely, but this is if we have too much condition, it will be infeasible. So we are going to set it as is. Is this all? Actually not. We need just one more thing, which is very important. Let's just import numpy as np. If you don't have numpy, probably this part is going to be the last part that we are going to cover before the break. If you don't have numpy, so that if you have an error, you can always hit install numpy like this later, okay? But you can just do it now. Random values. We are going to create the reason that we want to use numpy is because we want to create random values. Random values and how many random values? Like the snapshot, length of the snapshot, right? Multiplied by 20, which means inflow is gonna be somewhere between 0 and 20 megawatt, right? And then random inflow is gonna be Honda series random values. Index is network. You don't need to understand these two lines technically. It's just more about how to deal with the data set and how to deal with random data set, right? Much more important part is this network storage unit underscore T. This is very important because we are adding temporal data set, right? So we need to add underscore T. Inflow is PD data frame to where hydro reservoir and inflow. So I made another. Thank you. I already made some mistakes, which I would say intentional. No, it's not intentional. Huh? What happened? Oh, I missed S storage unit underscore T. Okay, we run it. There's no problem. We are going to run the model. And then the last part, what we want to see the output, right? We want to see the output. We need to see the generation output, which is network generators underbar T. Again, it's power. And let's copy it to make sure that we don't change the original data by mistake. And the output from the storage is gonna be stored in storage unit underbar T, and same power. We are going to copy it. And then we will put them together. There are many different ways of putting them together, but I always prefer PD concat, which is the simplest one. We are putting dfgen and df storage together in one data frame called data frame combined, df combined, using axis 1, so which is basically add side by side. And then we will print out. We will see the chart. Basically the same with the what we plotted before, area, and then it is stacked true, and big size is let's say 12 and 4. And if we run it, okay, here is the output. Compared to the previous one, right? We had gas 1, gas 2, and then wind, PV and wind, and small amount of bio, right? It's quite different because we have hydropower, which is pretty much zero cost, marginal price, which is marginal cost is zero. We have gas 1, gas 2, and then we have less amount of wind. Probably, I think less. Let's see, similar maybe, slightly smaller amount of wind, and then we have more hydro reservoir to follow up the peak, right? This is how the hydroelectric system worked. So, okay, this is what we are going to do so far. And then after about 10-minute break, we are going to add another storage unit, which is behind the meter, battery storage. And then we are going to calculate emissions. That will be the end of this today's session. Thank you. See you in 8 minutes. So shall we start? Is everyone here? If you are not here, please say so that I can wait. Such an old dad joke. We're gonna add another storage, okay? Basically the same, but let's do it by hand rather than copy and paste because we want to get used to. It's a storage unit. This time we are going to say battery BTM is behind the meter, but technically this is not BTM yet, okay? But I just named it as BTM. Bus is bus 1, so that it can be connected to the load. Is it load or renewable? I think bus 1 was the load, but can't remember. That's why you should not name bus like bus 1, 2, 3. You need to rename it with proper function to avoid this kind of situation. And but it's fine. Its capacity is 15 megawatt. We are going to set platinum extendable as forced so that it doesn't change the capacity. Max hours is 4 hours. This time, this max hours is very important because we don't have inflow, right? Compared to this is not hydroelectric power. This only store the charge and discharge the power electricity, right? So that we need to set the max hours. Capital cost is 50 underscore thousand, right? It's not comma. Please remember it's underscore. Marginal cost is 0. Marginal cost is 0. Efficiency for store is 0.95. So then 95 about it loses about 5% of electricity, and efficiency dispatch is 0.95. So it loses another 5% as well. State of charge initial is 50%, and then cyclic state of charge is true. So that, thank you. So that start and end point should be matched, right? And we are going to optimize it, and then we will see the output. Please type this in your code and let's run it together. Okay, I'm gonna wait about 30 seconds here so that everyone can follow. And then run it. It says it's optimal. And then interesting part is if we copy and paste some part from above, I'm going to copy and paste this for you on the chat. Let's get that part, and then let's try to run it. See what happens. It says it's error. There is an error, right? There is a red thing which doesn't sound too good. And in the end, it says when step is true, each column must be either all positive or all negative. It means the battery BTM, the P of battery BTM has charge and dispatch, charge and discharge, right? When it charge, it is represented or it is expressed as negative, right? Charging 10 megawatt of electricity is basically dispatching minus 10 megawatt of electricity, right? So it has plus and minus. When it has plus and minus, Python plot cannot plot them out and then ended up having error. So we need to add some more columns to deal with that part, but which is not too important at this stage. So I'm going to just share what I have already here. On the chat, you have another code which needed to placed between here. So what it basically does is it gets the information, the first part gets generator T's power, and then also gets the storage power as well. And then using these 4 lines, we are separating battery BTM's positive and negative into 2 different data frame. One is battery BTM discharge, and another is battery BTM charge. Right? And then if we plot it out, ta-da, we have much better result. Let's see. we have a gas, still we have gas 2 and we have gas 1, but we have battery charge and battery discharge here as well, bit of a pink one. But as you can see, there is a bit of an issue. Maybe there is a little bit of an issue that charging and discharging might happen together. I'm not sure. I didn't check it, but there are some there are some issues with pipes, but it can be easily solved by setting just one more constraint. But we are not going to cover that part here. I'm just telling you just to make sure that you notice that issue later when you found it. So what we covered today so far is covering the hydroelectric power, and then we saw the output. And then just before we added energy storage here, just to give you a brief introduction. Probably this is more like a review because we already created a code, but bit of theoretical background. Here is what it is. Storage operation and optimization is one of the most important thing that you need to understand and you need to be able to apply in the network when in the modeling work, particularly when you are dealing with renewables. I mean, in these days, even if you don't have renewables, having energy storage is quite critical because energy storage, this kind of energy storage can represent EV, electric vehicles as well. So using this storage unit, we can model charging and discharge of storage unit, including efficiency loss and also operational constraint as well. So basically, as you can see on the right side, we have discharge and also we have charging, which is negative. So for that, we added a storage unit, right? Later, after we we can try to have some different capacity, and then we will come back to the original value so that we will analyze how having different values can affect the result. So let's try to change some values here. We have two sort of a discussions that we can do. I'm gonna copy and paste those two discussions here. But please remember, we need to come back to the original code. So leave the original code as is, copy and paste somewhere or back up somewhere, and then try to change some values. First, what I want you to do is change the cyclic state of charge to false. And then probably you can set different state of charge initial, and then see how it goes. And then please share what you learned or what you observed with the others on page 16 of our slide. Okay? You don't need to change everything, but just try to change one of the thing and then, or maybe two things and see how it change the result. Maybe it is not very noticeable, but can be interesting. Again, when you change the value, what you need to use is override equals true. You need to add override equals true in the end of each component. For example, if you want to change some value of a, let's say, this storage hydro reservoir, for example, if you change this phenome extendable to true, you just do it, it says following storage unit are already defined and it will be skipped, right? It doesn't work that way. You need to add override true. Then it says nothing and just do the optimization properly. The second discussion is not going to be too easy, particularly the what happens if we allow hydroelectric power plant to charge from the grid. This is not going to be too easy to change the system right now. So probably you can have a look at it later after the course. If you make it happens, it becomes pumped hydroelectric power. So not too much different with the energy storage, but it deals with the water. Technically, they are the same, just energy storage, but different energy efficiency, I guess. So we have one observation changed the initial hydro reservoir, the state of charge initial of hydro reservoir and battery BTM from 0.5 to 0.2, but can't see any difference. Yeah, I can see the reason because as you can see from the beginning, the initial part, the beginning part of our how do I say, our network or our grid has a more energy that provided more energy supply than the demand. So demand is not really high, so that we have enough energy to be charged, right? So that I think that's the reason why there is no difference. But probably if we start the snapshot around probably 4 o'clock, maybe the things can be quite different. Maybe 3.5 or something like that. When there is a lot of demand, but not enough renewables, maybe things can be quite different. That's good. Thank you for sharing it. Here is another observation which changed a phenome extendable to true and max hours to 12. I think you changed it to a much longer battery and allowed to allowed a capacity expansion as well, which the grid or pipes are use the battery system much more actively, as you can see. This is interesting. And then there was a question from Faris. Yes, we can set the start time by changing the snapshot. So if we go back a little bit of our code, on the top, we set the snapshot here, right? So we can change the snapshot to something like this, or we can set the initial snapshot to this, and then we can change the snapshot to something else like this, right? There's another observation. This looks very interesting. Let me see this one. Change the max hours, hydro reservoir, and change the capital cost, and then also added some marginal cost as well, and then override true. Then what we have here is much more interesting electricity generation of hydro reservoir, which seems quite active. Up and down is pretty significant. That's interesting. And then also there is bit of peak as well. I can understand why there is a bit of peak, but I will analyze what happened based on this information, and then probably I can share it later. But this one is very interesting. Let me double check it later after the course. Thank you so much for sharing yours. And if you are still doing it, you can share it. Then I will have a look at it, and then we'll share. I will share my understanding later, probably in the next course. Okay. So what we are going to have is the emission, right? Emission is one of the most important thing because the basic reason why we are analyzing this power network is because we want to analyze the emission, right? Is that correct? I mean, we are not power model. I mean, technically, we are not power modelers and we are not grid operators. But we are from CSOs and NGOs. And the biggest interesting, I guess, is gonna be the environmental impact at this stage. I mean, can be different by people, by different and by group, by country. I don't blame it at all, but at least for me, emission is one of the most important criteria that we should analyze. So, how to add the emission? We PipeSat itself doesn't have the emission as a default value, but we can add it using carrier. We can set up carriers, and then in this case, for the carrier, we are going to set up for each carrier, I'm going to set up a CO2 intensity equals 0.4. We are going to set up another for bio to be 0.3. The unit is ton CO2 per megawatt hour. Right? And then we are going to add CO2 as a just a new like new column or new attribute to all generators equals network generators carriers um ah is there any way that I can probably this a little bit better? Carrier and either map network carriers to CO2. I mean, how to mapping it is not really important. The key is understanding that we are gonna have a CO2 as attribute. As we see here, in the last part, we have CO2. And we have 0.4 and 0.4 for gas 1 and gas 2, and 0.3 for bio. We don't have any CO2 for PV and wind, right? Total generation is network generators T underbar dot P sum. We're gonna see the entire power output as a total generation, and then we are going to estimate emissions by generator using total generation multiplied by I don't know how to remove those icons. Where is it? Where is generate tools? Thank you, Paulo. So then we can group them. Emissions by carriers. Emissions at the moment, what we are doing is just calculating emissions by carrier, by generators, and group. We are group them by carriers and then sum them up. So then we can have just one single beautiful value for each generator. And then we are going to print out emissions by carrier, but let's round it to. We see it. We have zero emission from bio, and we have a bit of emissions from gas, and renewables don't have any emissions. this is the output so far of our system. Can be slightly different because I already applied some strange numbers when I was working on the previous discussion part, and probably everyone might have a slightly different number. It's fine. But the thing is, what we did so far is based on the amount of generation, we multiplied the emission factor to the generation and then sum them up to a calculator to see how much of a generation that we have. Of course, there is a fantastic and beautiful way to print it out, but as the part is pretty long, I'm going to share my code to here. On the slide 19, I shared a long code which I tested and which works, which will show you a chart of this one. It's zoomed in too much. So we have dispatch and then emissions as well. So if we zoom in, we have gas. What is this red one? Gas 2, right? We have gas 2, and then we have gas 1 generation, and then we have a little bit of blue. What is this purple? Is PV, and we also have a wind and storage as well. So this is one beautiful chart, and then on the right side, the CO2, we can see the CO2 emissions. The emission of this system is about 25 ton per CO2 per every an hour. So average 25 ton is the emission of this system. But the thing is, if we go back to the slide, we defined emission intensity and we actually added, we understood how to calculate the emission, so that we added a attribute to CO2 to gas and bio, and then mapped the emissions to each generator and calculated it. But what's missing is, we analyze it, but what's missing is what happens, how can we limit the amount of emissions, right? The reason that we want to estimate the total emission is because somehow we want to limit the total amount of emissions of the system under a certain amount, right? Pipes doesn't have a default or doesn't have a off-the-shelf way of doing it, but there is another way to apply the limit or the constraint. So we can add, say, global constraint, and we will name it as a CO2 limit. And then we are going to set it as primary energy, which is basically we are applying this limit to the primary energy. Oh, I'm sorry about that. Is it fine? I zoomed it out because if I zoom it too much, then chart was not really showing. Chart was not really visible at all. So I changed it. And then carrier attribute, which means we are going to apply this constraint to CO2 carrier using below or equal than 5,000. So let me explain you. So we are creating entirely new component here, which is very important to understand. This is a global constraint, so that this constraint will be applied to the entire time frame or entire snapshot of the network, right? So that the name is CO2 limit, and we are going to apply it to the primary energy, to gas or to each like bio or etc. And then this is going to be applied to CO2. Carrier attribute is CO2, which is basically which is saying that we are applying this limit to the CO2 attribute, and then the value should be below or equal to 5,000. Which here unit is going to be ton CO2, and if we want it, let's see how it works. It becomes infeasible. Why is it infeasible? The reason is because the current system is not possible to provide enough electricity while meeting this, satisfying this global constraint, right? This is the problem of this entire network. Yes, exactly, Paolo, because the entire system has too much CO2. In the other way, we don't have enough amount of renewables, right? Yes, so that this system doesn't work. What we need to do is we need to understand how much of renewables do we need then. Then what we want to change is generators P norm extendable is true. Let these pipes are to decide the amount of generators while meeting or satisfying CO2 emission limit. Yes, we have the result, and I'm gonna copy and paste some of my code, which is exactly same with the plot code that I provided before. So gonna copy it from the slide and then see here. Okay, seems a bit weird, but what we need to do is just zoom in. Okay, can you see the difference here? I'm gonna see first 2 days. Okay, there is a big difference. We have bio, but where is gas? We have very small amount of gas 1 and 2, but we have bio, and we have more wind and hydroelectric power, and then we have battery as well. For some days, we have solar photovoltaic as well. This is the system that pipes think this is the most cost efficient while meeting the CO2 emission constraint. We can zoom it up a little more, like say about this much. And then when there is a very limited amount of gas and bio, as you can see, the CO2 emission is very limited, below about, I think below about 3 or 3.35. But then as we have more bio, each emission becomes higher, go up to 12, right? Interesting, right? That's what we Yes, that's what we actually can do. So this is very interesting to see how the system can be or should be totally different if we actually want to achieve zero emissions. So I mean, as a background in energy and power modeling, what I understand so far, based on my modeling works or experience, is based on the current idea or current concept. What I say is just a legacy concept. Is not suitable at all to achieve 100% 100% like non-carbon or zero carbon power shares or zero emission power network. This is not possible using legacy idea. We need entirely different system unless we rely on nuclear a lot, like France, then in that case, legacy system will work. However, if we want to achieve in a more sustainable way using renewables, then probably we might need something different and totally different approach in terms of energy storage, and in terms of grid, and in terms of our system planning process itself as well. So that's what I wanted to cover today. And our learning objective today was integrating solar and wind with time varying profile. And we actually successfully added hydropower as inflow based storage. Inflow here is not really amount of water, but it needs to be calculated as a megawatt. Usually, if you look at your own country's data, it is not too difficult to calculate or calculate megawatt from the amount of water inflow. If you can't find it, probably there are some other global data set from I don't know somewhere UN or something, because usually water inflow data is not something very difficult to find. It's quite easy to find. So yeah, it can be quite usable if you it can be easily findable. And then we modeled behind the meter battery at bus 1, and we tracked and visualized the CO2 emissions by carrier. And then we visualized we also added constraint, global constraint, which is totally new, new concept or new component. We added new global constraint to limit the entire amount of CO2 emissions below certain amount. Couple of things that you need to remember carefully is when you use hydro reservoir, you need inflow, and you usually need efficiency for dispatch and charge. In case of battery, definitely max hours is the most important one, because you cannot change max hours while leaving the capital cost as is, because capital cost is usually decided by the max hours of the battery. For example, if you have a battery which goes only 1 hour, then it can be $1,000, for example. But if you want to have a battery which can have a same power output for 4 hours, then the capital cost is going to be 4 times, almost exactly 4 times. That's how things how you need to assume when you model batteries. And we can add emissions, and we also found that emissions can affect quite a lot, and limiting the global emission, or limiting the amount of emission of the system, is going to change the entire power shares completely different way. Okay, that's what we covered today, and thank you so much for coming today's session. And from next week we have a special guest, and then we are going to cover some more interesting model using the real data of some selected countries, including Indonesia, India, Pakistan, South Korea, the Philippines, and Japan. So if I'm missing any countries that you are working at the moment, please let me know. And we are going to write a short report together. Thank you so much.